In this lecture, we are going to talk about that there are some restrictions on rotational symmetries uh, in a lattice or a crystal. So let's look at what do I mean by this. And this restrictions that come are due to presence of translation symmetry. Let's take one specific example first and then we will generalize the situation. Consider a five-fold rotation symmetry. Now, what it means is that minimum angle through which I need to rotate is 2 pi upon 5 and which is equal to 72 degrees. Now, let us consider a row of lattice points. Equally spaced lattice points. And let us say that at every lattice point I have a four-fold rotational axis. So, let me just take, let us say I will take this point A and point B. It has five-fold rotational symmetry and the spacing between these lattice points is, let us say it is T, basically the translation magnitude going from A to B. Now, at every lattice point in this I am saying that I have a five-fold rotational symmetry. Therefore, let me give a 72 degree rotation about these points. So, if I give a 72 degree rotation about point A in the counterclockwise direction, then I will take the symmetry will operate over entire space, it will operate on all the lattice points. So, therefore, it will also operate on B. So, it operates on B and this lattice point at B is taken to, let us say, a point C. So, point C is also a lattice point. Now, if I give a rotational symmetry by giving a rotation of 72 degrees in one direction, I will also have a rotational symmetry by giving a 72 degree directions in the opposite case. So, here I have rotated in the counterclockwise direction by 72 degrees. At B, I give a rotation of 72 degrees in the clockwise direction and I will end up generating a point D. What has happened is it has taken the lattice point at A to the position D. So, C and D both are lattice points and A and B, as we had said, are lattice points, and here I have given a clockwise rotation of 72 degrees. And let me join C and D as well. So, let me write that I have A, B and then I also have C and D to be lattice points. Now, from this diagram, AB is the minimum distance between lattice points, because it is a distance between two adjacent lattice points. So, in the direction of AB, I take any other direction in the lattice, the minimum distance cannot change. Now, consider I should write that AB direction is parallel to CD. Therefore, I should get the same spacing along what the spacing that I get along AB direction, the same spacing of lattice points I should get along the CD direction as well. So, same spacing of lattice points in both cases. But as you can see from the diagram, that clearly CD is less than AB, and this is a contradiction. That I cannot have lattice points located at C and D if I have lattice points at A and B. And this gives me the conclusion that five-fold symmetry cannot exist in a lattice. So, this is just one specific case, but let us generalize this case a bit and then figure out what are the rotational symmetries that are possible in a lattice. And this restriction is coming as a result of the presence of translation symmetry, because if we were to accept that C and D are also lattice points, then I break the translation symmetry of the lattice. So, let us take a more general case now. Let us say I have again two lattice points which have a certain spacing, and each of them, let us say, has a rotational symmetry with that minimum angle of rotation, let us say, is alpha. So, I am going to call this as A sub alpha, B sub alpha, and I have the rotational symmetry on the lattice point. Again, as before, the spacing between the lattice point is or the length AB is T, and let me give a rotation of alpha about A, which will take the lattice point B to and generate another lattice point. We will call that lattice point as C, and this angle is alpha. Similarly, I give a rotation of alpha at B, but in the opposite direction, in the clockwise direction, and this would give me, it will take the lattice point at A and generate another lattice point at point D. And this C and D can be joined with a straight line, and you can see clearly that AB has to be parallel to CD. Now, let us look at this diagram and try to analyze what is the distance between the points C and D. In order to do this, so let me draw a small construction here, draw perpendiculars from A and B onto the line CD, and let us say these perpendiculars meet at points E and F. So, I can write now that what is the distance between the lattice points C and D, or what is the length CD? The length CD would be equal to CE plus EF plus FD. And let us see what is CE, EF and FD. EF is very clear that EF has to be T. CE, we need to know, we will look at the triangle ACE, and we need to know what is this angle. This angle is clearly pi minus alpha, because the angle CAE is alpha minus pi by 2. From that you can figure out that the angle ACE would be pi minus alpha. Similarly, this triangle, the angle FDB would also be pi minus alpha. So, CE becomes, now another thing, AB is T. When I gave a rotation of A, this entire line AB basically rotates to form AC, and hence this length AC would be T. Similarly, the length BD would be T. And therefore, if we look at triangle ACE, CE becomes T cos pi minus alpha, EF is T, plus FD will be the same as CE from the triangle FDB, and that is T cos pi minus alpha. This will give me essentially T minus 2T cos alpha, which is T into 1 minus 2 cos alpha. Now, since C and D need to be lattice points, because A and B, we started out with A and B being lattice points, CD must be equal to an integral multiple of the translation from A to B. So, some integer m times t, and this would be equal to t into 1 minus 2 cos alpha. So, this will get cancelled and we will be left with, and rewriting the equation, I will get cos alpha would be equal to 1 minus m divided by 2, where m is a integer. Now, let us see, looking at this particular equation, let us try to figure out what is the implication of this equation. So, what we will do? We will put in different values of m and find out what is cos alpha, and then find out what is alpha, and that should give me some insight into the symmetry, rotational symmetries. So, let me make a small table. Okay. So, we can take for m negative numbers as well as positive numbers. Let me start with minus 2. Now, I plug in minus 2 in this equation for cos alpha. So, I will get cos alpha to be 3 upon 2. Now, cos alpha value can vary between minus 1 and plus 1. It cannot exceed. Therefore, this is an invalid value for cos alpha, and hence you can't calculate any alpha for that. Let us take another, and if I try to take more negative values like minus 3, it will become even more larger than plus 1, and hence not possible. Let us try minus 1. If I put minus 1 in this, this will become 2 upon 2, which is 1, and alpha can be 0 or 2 pi, but we will take 2 pi. If I take value of m to be 0, then cos alpha would be half. So, half means alpha would be 60 degrees or pi by 3. Now, let us take plus 1. Plus 1 means cos alpha would be 0. Therefore, alpha has to be pi by 2, 90 degrees. Now, let me take 2. If I take 2, cos alpha becomes minus half. Minus half means alpha should be 120 degrees, which I can write it as 2 pi by 3. M equals 3, put it 1 minus 3. So, that would give me minus 1, and minus 1 means alpha would be pi. If I take m equal to 4, then this will become minus 3 by 2, Now again, now this value has gone less than minus 1, hence this is again an invalid value for cos alpha. So, we can't have any alpha for that, and subsequently larger numbers would lead to more and more larger negative values, and hence those are not valid. So, the only possible values of m are going from minus 1, 0, 1, 2 and 3. So, let us look at now what this alpha is going to tell me. Well, this 2 pi, for instance, I can write it as 2 pi upon 1, pi upon 3, I can write it as 2 pi upon 6, pi upon 2, I can write it as 2 pi upon 4, and this is already written in that form 2 pi upon 3, and this I can write as 2 pi upon 2. What basically this is telling me, it has calculated the minimum values for alpha for a given n-fold axis, and hence I should be able to write that 2 pi upon 1, this gives me 1-fold rotational axis, 2 pi upon 6 gives me 6-fold rotational symmetry, 2 pi upon 4 gives me 4-fold rotational symmetry, 2 pi upon 3 gives me 3-fold rotational symmetry, and 2 pi upon 2 gives me a 2-fold rotational symmetry. So, what we have worked out from here, these are the only rotational symmetries possible. So, in conclusion, only 1, 2, 3, 4 and 6 fold rotational symmetries possible in a lattice or a crystal. If there was no translation symmetry, then one could have any value of n, and in fact in nature you will see that you have many more rotational symmetries. If you look at some plants, you can find, you can look at some flowers, even 5-fold rotational symmetries and 8-fold rotational symmetries and so on. So, these I will also refer to as crystallographic rotational symmetries. And lastly, let me also write down, we use certain graphical symbols for these different rotational symmetries. So, 2-fold, 3-fold, 4-fold and 6-fold, and you can see that there is no 5-fold. Now, a graphical symbol for this is a kind of a lens, or we can even say an ellipse, that is used. And in fact, in the previous lecture, when we had looked at the various rotational symmetries in the lattice, this was a symbol that we had used. For 3-fold, a triangle, well, we know that equilateral triangle will possess a 3-fold rotational symmetry, that is 120-degree rotation. 4-fold clearly is a square, again we had used it in the last lecture when we are depicting the rotational symmetries in the lattice, and 6-fold is simply a regular hexagon. And in fact, if there was a 5-fold symmetry, then one would use a regular pentagon, but let me just remind you that this is not crystallographic.